Hello and welcome to the Oxford Online Maths Club, Season 3, Episode 0. My name's James and I'm the Admissions Coordinator for Maths at Oxford, and today we're going to talk about some math stuff. Great to have you with us if you're watching live. Hello to people in chat as well. Hi to Abakar, Georgie, Pen, Molly and SV. I can see on screen at the moment. If you're watching live and you'd like to join the live chat, there's a link at the bottom of the screen. Two things I've got to do at the start. Firstly, this is episode 0. It's a sort of tech test, so if stuff goes wrong, it's because I set up some new tech and we're trying to see if we can get things to work on that. Hi to Simon, hi to Alex, hi to X plus IY, hi to Raf. Secondly, I've seen some audience retention stats, and most people don't make it past the first 30 seconds of our videos, so if that's you, then thanks for watching and I'll see you next week for the first 30 seconds of that one as well. YouTube's a very, very strange thing. We're combining together some strange, weird tech that I don't fully understand with YouTube, which I don't fully understand. My name's James, let's go. Right, okay, hi to Raf, there we go. Good. Hi to Darishley. I should say, if you haven't seen this before, we're using Slido live chat because it lets you be anonymous without signing into YouTube or Google stuff. Because it's anonymous, you can stay anonymous, like this person who's joining for the first time. Hi, nice to have you with us. Or you can set your username to your name or a famous mathematician's name if you want to. Good. Happy New Year to everyone and Merry Christmas. Happy holidays, everything like that. Cool. Somebody set their username to Oxford Reject, which is a bit sad. And they've said, "What up?" which is quite happy. So that's a kind of mixed emotions there. Hi Esme as well. Right, cool. Okay. There is a slight delay between the chat and the video. Anyway, people have aware of the idea of stream lag, right? Always trying to reduce stream lag. Okay. I've slightly redesigned before we get into the maths. I've slightly redesigned. Look. There's now a bigger screen for maths. I can put maths anywhere on this screen. I think it's about 1.5 million pixels of maths, all of which are currently blank. So that's terrifying. Hi to Ben. Anonymous says they're nervous for Tuesday, which I think is an Oxford thing as well. And somebody's said something about interviews. Right, okay. Chat's off and away. Nice to have you with us, chat. Nice to have people here. I've already got a warning message from YouTube, so that's the tech setup, I suppose. People will tell me if things break, right? If they haven't heard anything or seen anything yet, then maybe they're still waiting for us to go live. Anyway, cool. Coming up today, we've got shapes. I'd like to show you some shapes that I've got here on my desk. Then I'd like to talk about patterns that we can spot between those shapes. So that's the plan. I'm going to show you some shapes. We're going to talk about some numbers to do with those shapes. I'm going to try and look for patterns wherever we can find them. Okay, hi to an anonymous person who's just joined us as well. Good, that seems to be working. Computer's not on fire, everything's good. Right, cool. So someone's just said they've got a newfound love of geometry over the holidays. They might be into this. I've brought some shapes along. I think I've talked about these on various things before. If you've seen Maths Club Season 1 or 2 from last year, or if you've come to Maths Talk, so you might just have heard about these anyway. What I'd like to talk about for at least the first half of today's Maths Club session is the Platonic Solids. I'd like to show you the Platonic Solids. I thought that slide was going to say Platonic Solids, can you tell? Instead it says, further reading is posted on Friday on the website. It's www.maths.ox.act.uk/r/club. How can I forget? After every live stream episode, we put up further reading for more stuff related to what's happened in the live stream on Thursday. That goes out on Friday, so if you check the club website, you can find out more. It's also where you get the replay of the video. It's all coming back to me from seasons 1 and 2. I don't know if you can tell, but it's coming back to me, the sort of stuff that you say during one of these Oxford Online Maths Club things. Anyway, Platonic Solids. There we go. There's the slide I was expecting. There are 5 of them. I would like to show you the 5 Platonic Solids. Now, maybe you've already heard of the 5 Platonic Solids and you know what's about to happen. I'd like you to try and imagine or pretend that you've forgotten what they are. To try and imagine you don't already know what Platonic Solids are. And if you don't know what Platonic Solids are, if you don't know what those words mean, brilliant. Just the sort of person I wanted to watch this. We're going to find out. Okay, to do this, to show you these Platonic Solids that I've brought along, I need to switch to a new bit of tech, which is desk cam. Oh, desk cam is working. No, it's not. Hasn't appeared on screen yet. Desk cam. There it is. Desk cam. Ah, that's working. That's brilliant. Apparently Slido's updated as well, so new fresh software everywhere you look. Okay, so I've brought along 5 Platonic solids. I'd like to show them to you one by one. Maybe before I show you each one, I'm going to describe it, and you can try and imagine it, because somehow imagining what the shape is like before you've physically seen it is perhaps a good exercise. And if you've already heard of Platonic solids and you already know what they are, you can try and work out which one I'm describing. Okay, so I'm holding the first one. I'm holding it by 2 corners. It's got this pair of opposite corners that's handy to hold it by, and I can see that it's got about 6 more corners in a zigzag pattern around the middle between the 2 corners where I'm holding it. So I'm holding it by 2 opposite corners, and then it's got 6 more corners around the middle in a zigzag pattern, zigzag pattern up and down. Half of them are connected to the top corner, and half of them are connected to the bottom corner, alternating up and down as you go round. Can you imagine that shape? Well, if you can imagine that shape, give yourself a pat on the back, because here it is now. Okay, so I'm holding it by that top corner and the bottom corner, and then it's got 6 more corners on the way round. Half of them are joined to the top corner and half of them are joined to the bottom corner. And hopefully you've already realised that I've pulled a trick on you, because this is a cube. And probably the normal way you would describe a cube is not the way I described it, with a top corner and a bottom corner and 6 corners in between. But look, it does work, right? It does have that property that you can choose 2 corners and then the other 6 are half of them connected up and half of them connected down. That is a description of a cube. I'd quite like to know how you would describe a cube. Probably not like that. Maybe let me know in chat how you would describe a cube. I've got some ideas about what you might say, but I'd like to know what you would say. Cool. Okay, I've put it there. This one's got the faces numbered, which is helpful. It's got the numbers 1, 2, 3, 4, 5, 6. So this has got 6 different faces. Okay, and I suppose 8 corners, because there's that top one, the bottom one, and then 6 more around the middle. Okay, that's kind of interesting. So it says by its net. So that's a good idea. The net is what you get if you took the faces and you unfolded them. Maybe you were explaining to somebody how to make one of these out of cardboard. So you might show them the net and explain how to fold it up. I suppose that's one way of describing a cube. It's actually got quite a few different nets that you could show. There's an interesting question there about what all the nets are of a cube. A whole load of right angles. Yeah, I suppose it has got a lot of right angles, doesn't it? Because well, it's got these sides as squares, and they kind of join up at right angles as well. A whole load of right angles. Somebody's called it the only hexahedron. I was hoping somebody would say hexahedron, which is a kind of Greek construction word, I suppose. Hexa for 6 and hedron for faces. Nice. A shape with 6 faces. Opposite faces are parallel. This is a good description, I like this. Adjacent sides are perpendicular. So this is the right angle idea again. That whenever you've got 2 faces, they're at a right angle. I'm trying to show you that right angle. There we go. Okay, I like that too. Millie says, hang it out by one face and describe all the other faces in relation to that face. Yeah, I quite like that. Ben says it's got equal length sides, which is true about that shape. Yes, it's got all sides the same length. Why not just its faces? Yeah, so if you just say it's got 6 squares, just take 6 squares and glue them together. Well, I feel like when we're gluing the 6 squares together, the idea of the net telling us how to glue those squares together is kind of important, right? It's like the assembly instructions of how to put together those 6 squares. The kind of IKEA diagrams of where to put your squares together. Yes, it does have a line underneath the 6, just in case you thought that was you'd maybe rolled a 9 on this 6-sided dice. No, it's a 6. Good. SV has got a description. They've said R3 in this, which means R3 is a shorthand for 3D space, I think, in this. All the points in 3D have coordinates in 3 continuous ranges. So some sort of interval thing going on to say, well, the cube starts here and it stops here, and also in this direction it starts here and it stops here, and in the Z direction it starts on the table and it stops here. I quite like that as well, intervals different continuous ranges for x, y, and z, that is where the cube is. Fair enough. Okay. Could you describe a cube by the shape or different shapes that are casted by its shadow? I think there's a recent 3 blue, 1 brown video about shadows that you get from a cube. You can make different shapes from its shadow, and I guess there's an inverse question there. If I show you the shadows, can you work out that it was a cube? I think questions like that are pretty tricky, because, well, you've got to piece together a lot of information. It's like me describing it in a funny way, but even worse. Squared square and a 3D tesseract. I feel like people have met this idea of putting lots of squares together. Define it using some sort of Pythagoras thing. Okay, some sort of distances with some straight lines. Nobody said this yet, but maybe it was implicit in the 3D stuff that you could talk about the coordinates of where the corners are. So you could write down coordinates for where the corners are. Everybody take a moment. I know it's after 5 PM on a Thursday and we've all had a long day, but let's take a moment to think about where we would put those coordinates for the corners of a cube. Let's not write it down, it feels like a lot of work. Yeah, okay, we've all thought about where we would put the corners for a cube in coordinates. Oh, you can work out the surface area. Oh, right, okay, cool. Good. I need to watch the 3 blue 1 brown video. I haven't. Confession, I haven't watched it all yet. Okay, it's exciting. Cube. And people have now got facts about cubes. 2 hands about to clap. Can't tell if that's. Oh, like 3, like these 3, like a hand? I don't really know. And those 3 there. So it's sort of like 3 faces. You can kind of hold it with 3 faces like that. And then there's 3 more faces on the top. It's not a mad way of describing. Not a mad way of describing a cube. Right, okay. That's the fun I've got out of a cube, and I've got 4 more to go, which are, if anything, more interesting. Okay, I'm going to try and describe this next one in a less stupid way. So next one I'm holding, it's got 2 opposite points that I'm holding it by, and it's got some more corners around the middle, and all of those corners joined to the top and to the bottom, and the shape is made out of triangles. It's made out of 8 triangles, and it looks like this. I just pointed to the cube again as if the cube was the thing that's made of triangles, but no, it's this shape. And somehow when I look at this one, I don't know if this is a human biology thing, but when I look at this one feels more pointy. It feels more like the description of it having a top point and a bottom point and things in the middle makes more sense. But I think that is a human biology, kind of psychology sort of thing, that this one feels pointy, and I should describe it in terms of its points. But I could describe it in terms of its faces instead. So the faces here are these 8 triangles. Oh, if I do that, you can see the light on the triangle. That's nice. I could describe it in terms of its triangles, I suppose. There's a triangle at the top, and 3 triangles attached to it. Okay, and then opposite that, there's that same structure again. 1 triangle in the middle with 3 triangles around it, and then those 2 shapes are very neatly glued together to give me this thing, which is, it's not quite a triangle prism, but it's what you would get if you took a triangle prism, put a twist in it, and then joined up everything the other way around as well. That's not a great description so far, is it? Okay, that's got 8 faces. It's called an octahedron. Octa, 8. Octa. Hello. The angles are smaller, aren't they? There are ideas about it's made of triangles which have smaller angles than the squares, and also the top really is pointier than the cube is. There's some ideas about how you might define 3D angle, but yeah, the top corner takes up less of a kind of sphere than the corner of a cube does. So it is genuinely pointier. Right, cool. That has nothing to do with D&D. Today's session has nothing to do with D&D. I just happens to have this collection of polyhedra because of maths. Oh my word! So something about Manhattan metric. I feel like this is back to Pythagoras as well. People talking about different distances that you could define. There's some sort of strange notion of distance where if you choose that as your notion of distance, then this thing turns out to be a bit like a sphere. Maybe that gives you an idea about how weird that idea of distance is, that this could be the answer for what a spheres look like. Right, okay, good. radians are defined by how they subtend link. Could you have a 3D angle based on area? Yes, that's called solid angle. The idea being, if you put this at the centre, you put this at the centre of a sphere, and you think about how much of the sphere is inside this angle. So you just take a little sphere. Don't worry about the rest of the shape. Just look at this angle here. If you put the centre of the sphere on the point, and you think about how much of the sphere is inside this angle, 3D angle, that gives you a way to define how big angles are for solid 3D angles, which is useful if you want to define pointiness. Okay, put that one there. Good. Does anybody want to define pointiness? I feel like we said pointiness, or said it was pointy so many times that definition might be handy. Okay, which one am I going to do next? We've got two so far, and I still haven't told you what's going on, I suppose. Still just a collection of shapes that I've got. The next one I've got is constructed from edges. It's got one edge, and then opposite that edge, it's got another edge that's going in the opposite direction. Okay, so if you imagine that, two non-intersecting, non-parallel right-angle edges, one on top going one way, and one on the opposite side going in the opposite direction. And that's about it. That's all of the vertices, at least. It's got a few more edges just to join everything up, to join both ends of each of those edges to each other. But that's all it is. It's a pair of lines, pair of edges that have been joined up. Cool. People are now playing the game, which is what I just due to the stream lag, it was a little bit tricky to play the game, but people are now playing the game. Yeah, this one's Tetrahedron. Okay, so there's its top edge between 1 and 3, and here's its bottom edge for the even numbers between 2 and 4, and then that's pretty much all of the shape, because the only other thing that's going on is that the top edge is joined to the bottom edge to make this shape. So the game we're playing here is Platonic Solids described badly. Can you work out what on earth I'm describing? Because the rest of the edges, you just join up that top edge to the bottom edge. Okay, of course that's not how most normal people would describe a tetrahedron. This is more, I think, better described as a triangle-based pyramid, or if I hold it like this. So it's got some triangles going on, all the faces are triangles, and it's 3 triangles stuck onto one base triangle. The desk cam is a little bit awkward because it is not mirrored. I keep expecting it to be mirrored, but it's not mirrored. Right, okay. Mystery Platonic Solids. Brilliant. So triangle-based pyramid. This is quite a nice one. It's probably the pointiest thing we're going to see today. Okay. Notice here for dice designing, this one's got the corners labelled instead of the faces, because its faces aren't parallel with opposite faces. It doesn't really have enough faces to do that. Anyway, okay. So this one's been labelled in a slightly different way. It's had the points labelled instead of the faces. Okay. 2 to go. I'm going to speed up a little bit, partly because these ones are much harder to describe. Which ones do I want to do next? Next one's my favourite. It's entirely built out of pentagons, and it's been built out of 12 pentagons that have been glued together along the edges, with 3 pentagons meeting at each point. It's the dodecahedron, which looks like this. So it's got 12 of these pentagons. Yeah. Stream lag means I'm going to win every time. There we go. There, you see. You did beat me to the punchline. Cool. 12 of these pentagons glued together. So here I've got a pentagon at the top, and other pentagons stuck to it, going around. I really like this one because so far we've only seen shapes made out of triangles and squares. Triangles and squares get a lot of airtime because they tessellate the plane. You can put triangles and squares together to make nice floor patterns and tilings like that. Pentagons don't get a look in over there. So I like that this shape's made of pentagons, and it's nicely symmetric and kind of beautiful that there's 3 pentagons to each point. Okay, good. There we go. One more to go, and it's what happens when you take every face of the dodecahedron and replace it with a point, and you take every point and replace it by a face. So if you imagine putting a point in the middle of each face of the dodecahedron, this complicated shape made out of pentagons. So you take this dodecahedron, a point in the middle of each face, and then join up the points, putting a line between 2 points if the original faces met in an edge. So this point at the top would be joined to these 5 points around it, but not joined to the point on the other side. Okay, if you can imagine that, then I think you are imagining this shape, which has got here a point at the top, and that's linked to these 5 points around here, and on the other side there's a different point that's linked to 5 points around there, and that gives a total of 12 vertices, the corners of the shape, and 20 faces. So that gives you this shape, which is called an icosahedron. It's got 20 triangular faces. I suppose if you're constructing it like I just did from the dodecahedron, they're triangle faces because each point of the dodecahedron has 3 pentagons. So when I replace the faces with points and join them up, I get triangles. And I suppose the nice thing that you do here is that you can go back the other way again. If you take the icosahedron, this shape with 20 triangles, and you put a point in the middle of each of the faces and join those up with the same rules, well, you've got 20 points. If you join them up with the same rule, joining 2 points if the original faces shared an edge, you get back to the dodecahedron. Cool, right. It's aphantasia, the thing about not visualising shapes. Sorry, this game was not fair on you. Okay, so these are called Platonic Solids. There are 5 of them, and I think it's only fair that at some point I tell you about what a Platonic Solid is. Raphael, great question. So a Platonic Solid, maybe you've noticed the nice properties that these shapes have. They're 3D shapes, they're made from 2D faces. The faces are regular shapes. So here, triangles, we've got some squares, and we've got, this one's made of pentagons. Each one's made of regular polygons as the faces, where all the polygons are the same and they're all the same size. And also the way that those polygons are joined together is the same at each vertex. So there's always 2 faces meeting in each edge, but there's always the same number of regular polygons meeting at each vertex. Okay, so here there are exactly 5 triangles meeting at each vertex. Over here there are 4 triangles meeting at each vertex. This one is 3 squares meeting at each vertex. Those are the rules for being a Platonic solid. You need your sides to be a regular shape from the 2D world, and you need to have all of your corners the same. Okay, good, yes. Okay, those are all the rules, and those are all the Platonic solids. I think I'd like to work towards a proof of that if we've got a minute. So people switching the people talking about joules first. Okay, I'm going to give a moment for chats to catch up, and Spider-Man's here, so that's nice. So there's a question about switching the joules. So there's this operation called taking the joule, D-U-A-L. Well, I suppose as an adjective, these shapes are called dual polyhedra, because, here's the operation again, if you take this one and you put a point in the middle of each face and then join those up with an edge if the 2 faces shared an edge in the original shape, so here you'll end up with 12 points joined up in some way, and that gives you this shape. And if you do that operation in the other, if you do that operation, you get back to the other one as well. There's another dual pair hiding in here. I can't remember if I described it like this or not, but the cube and the octahedron are also duals. The octahedron is what you get if you replace every face in the cube with a corner, and you replace every corner with a face. It's sort of swapping faces and corners. Let's have a look at that. I'm going to try and hold them so that you can see that there's a corner of the octahedron, a vertex of the octahedron, wherever there's a face of the cube, and vice versa. Okay, I guess like that. and then I can sort of rotate them like this. Is this convincing? I can't really tell. Like that. Try and hold them so that they're kind of parallel. There we go. Cool. So those are also jewels. The cube is what you get if you replace the faces and swap the faces and vertices of the octahedron and vice versa. The lonely tetrahedron is its own jewel. If you swap all the faces for vertices, you get 4 of them, and you join them up, and you join all of them together, and you end up with a tetrahedron the other way up, I suppose, but you get a tetrahedron back again. So the 5 of them come in these kind of pairs, well, 2 pairs and 1 not a pair. Okay. Good. Yeah, so good. Okay. Does the dual process always go back to the original shape? Yes, I think so. What you're doing is you're swapping 2 things, so when you swap them, you get back. That was a terrible proof, but the right idea. And I think you can imagine doing this on other polygons, other polyhedra as well. If you can imagine other polyhedra, perhaps they've got a more complicated configuration of triangles and other shapes going on, or maybe loads of squares in some interesting array. You can do this swap on those polyhedra as well to generate new polyhedra. Okay. As I was talking before, I realised that the square rule, putting lots of squares together, but the rule about having to have all the corners the same is the only thing that stops us from having loads of interesting shapes that are just easy to build, because cubes are quite easy to use as building blocks in something like Minecraft or something. You could imagine building stuff out of cubes, and then well, I guess all the edges would be the same, all the faces would be squares, but sadly rats, the corners are not the same. So there we go. Okay, that process is called, what is the process called? I think it's called taking the dual. I'm going to try and look that up. No, that's not quite what it's called. Maybe it's called duality? I think it's called... I'm going to go with duality, and I'm going to put something in the further reading notes on Friday, so that if you're interested in the concept of dual polyhedra, DUAL, then there's links to click on and things to search for. This is the purpose of the Friday further reading. It's stuff that I didn't manage to say properly live. Okay, cool. Right, Platonic solids. Right, what am I doing next? I think I wanted to talk about the numbers of faces, vertices and edges that they've got. This is all of them, by the way. This is all 5. I think I'm going to prove that after the break. First, I want to show you back over here. I want to show you this table that I've made of vertices, the numbers, some characteristics about them, the number of vertices, edges, and faces that they've got. Because there's something interesting going on with all of these shapes that people spotted, well, hundreds of years ago. These shapes were known about to the ancient Greeks, and actually they did find all of them. Unlike sort of planets, where they were also interested in planets but couldn't find all the planets, they did find all of the Platonic solids. I think they had some sort of mysticism around what they mean. Do they line up with the elements? It's very exciting that there's only 5 of them. And then I suppose it took hundreds of years before we came up with a kind of more general theory of how shapes like this work. Are there only 5? Okay. Yeah, good. People are still defining pointiness in chat, which I like. Okay, so there are some rules here about vertices, edges and faces that I'd like to explore. Something that all of these shapes do, and I'm not quite sure how you'd spot this. I've listed out here how many vertices they've got. I'm going to call that V. How many edges they've got, E. I went and counted all the edges, and how many faces they've got. But there's this sort of slightly weird fact that for all of these, if you do V minus E plus F, so number of vertices minus the number of edges plus the number of faces, then you get 2 in each case. So that's sort of a super exciting observation. You know, we've got these weird 5 shapes, and all of them have this property that v minus e plus f is equal to 2. Those things are equal. Somehow, whenever you build one of these shapes, you know, v minus e plus f equals 2. Okay, and it sparked some sort of investigation in the 1800s, looking for, well, what other shapes is that true for? Maybe I'm not just interested in Platonic solids. Maybe I'm interested in other polyhedra built out of squares and triangles and all sorts of stuff. When else is this true? What other shapes can we say that about v minus e plus f is equal to 2? When you're doing this sort of investigation, you're sort of trying out, you know, get out your box of squares and triangles and try gluing them together to make a polyhedron, and then count all the vertices, edges and faces and see, well, hang on, does that still do this thing, v minus e plus f equals 2? And in a lot of cases, it does. It comes back to being v minus e plus f is equal to 2 as well. So people trying to work out what sort of shapes this works for. Somebody in chat has said this only holds for convex polyhedra, which is a tricky thing to say because you've used the word convex, which I think not everybody knows, and also this is false. It's not just true for convex polyhedra. I'm going to define convex just because you've said convex. A convex polyhedra is one where you take any 2 points and the line segment between those 2 points in your polyhedra is also in the polyhedron. So it's not a kind of C shape. Cool. Right. So there's actually a really complicated question about which shapes does this work for. Yeah, something to do with graph theory, something to do with holes. Yeah. Okay. Good. So I think what I want to do next is not prove that and not tell you which shapes it's true for. V minus e plus f is equal to 2. I think I want to do a quick proof that if that's true, there's a little bit of mathematician sneakiness, if that's true, then these are the only 5 Platonic solids. Okay. This thing's got a name, by the way. This v minus e plus f equals 2. This is called Euler's polyhedral formula. For a convex polyhedron, so that's that word convex for any 2 points. The segment in between is also in your polyhedron. For a convex polyhedron, v minus e plus f equals 2. So this includes lots of stuff that's not a Platonic solid, that's made out of maybe a mix of squares and triangles and pentagons and irregular shapes joined together. Okay. Good. Right, okay. So I think I'd like to prove that we've only got 5 Platonic solids if we assume Euler's polyhedral formula. How on earth am I going to do that? Right, okay. I'm going to do that, and I'm going to do that. Okay, and now I've got a whiteboard that I can write on. Cool. Okay. So here's the mission. Assuming v minus e plus f equals 2, there are only 5 Platonic solids. Okay, I hope that makes sense as a mission, even though I haven't convinced you at all that v minus e plus f should be equal to 2. So if I assume that, which is some sort of mysterious fact that seems to be true for all the Platonic solids we found, so maybe it's not unreasonable to think that maybe it would hold for any more Platonic solids. Given that, there's only 5 Platonic solids out there. Okay, so reminder, Platonic solid has all the faces are the same regular polygon, and there's a fixed number meets at each point. Okay, that's my mission. Put that there. Okay, here's how it works. I'm going to imagine a shape. Maybe it's made out of triangles, but loads of them. So here's my shape. It's got absolutely loads of triangles. That's 6 triangles, isn't it? Which is probably not a good definition of loads. But it's got loads and loads of triangles going on. Let's put some more triangles in. There we And at every point there are 7 triangles or something mad like that. Let's give those things some names. I'm using faces with n sides, so I suppose they've got n corners. And my sides are n-sided polygons. N corners. And I'm going to say that I've got, with m of them, meeting at each point. Okay, so by the rules of being a Platonic solid, I've got to do something like this. I've got to use a regular face, and I've got to have a fixed number, I'm calling it m, of how many meet at each vertex. So I've given those things names. Now let's write down some equations. I think that I've got, well, how many edges have I got? Maybe that's a tricky question. If I do that, how many edges do I end up with? Well, I suppose I don't know how many faces I've got at the moment, so maybe I'll give that a name as well. Maybe I'll say I've got F for the number of faces. So maybe I've got F for the number of faces, and each face has got n sides, so that feels like I've got F times n for my number of edges, because I've got, look here, I've got, how many triangles have I got, for example, and triangles have got 3 sides, so that'll be how many edges I've got. Oh, but wait, each edge is shared between 2 faces, because they've been stuck together along the edges. So I should take that and divide by 2, because if I just take each face and I multiply by how many faces, multiply by how many edges they've got, then I'll have double counted every edge, because I've counted it once on each side. Okay, so I've got this equation for how many edges there are. Okay, and how many vertices are there? So you can do a similar argument to say that I should take the number of faces, I should multiply it by how many corners they've got, but then divide it by m. So m was how many of them meet at each vertex. And that's a similar sort of over-counting argument, where I'm thinking about taking all of my faces, maybe they're all triangles, and working out how many corners there are in total in my big bucket of triangles. Well, so for the icosahedron that we had, there were 20 triangles, so that would be 60 corners. But the shape doesn't actually have 60 corners, because the triangles have been stuck together, with 5 triangle corners meeting at every vertex of the polyhedron. So I need to divide by 5 to work out that the icosahedron actually had 12 corners, vertices. Okay, so this is a similar sort of argument to work out how many vertices there are. Quick look at chat. Raf says, I don't understand what a Platonic solid is. They're just regular polyhedra that have been made out of regular polygons glued together with a simple rule for how many of those regular polygons you have at each point. Each face is a convex regular polygon. So for example, triangles or squares, the ones you know, stuck together with the same number meeting at each corner. Like how the cube is made from squares, the squares meet with 3 at each corner. That's what a Platonic solid is. You've already seen all of them, there are only 5. This is some confusing. Cool. Okay, good. What are we doing? We're going to, at the moment, I think I'm just writing down facts. You know, we've got these facts about how Platonic solids work. I've given the variables names. I've tried to work out how many edges and vertices there are in terms of those things that I gave names to. F for my number of faces, N for how many sides the face had, and M for how many faces were meeting at a vertex. What am I trying to do? Well, I'm trying to work out, if I assume that Euler's right, that V minus E plus F equals 2 for all of these Platonic solid sort of shapes, because Euler says that this is true for a big category of shapes, then maybe I can work out facts about my Platonic solids. I can work out facts about N, M, and maybe also F, E, and V. I can work out what these shapes are. Okay, let's try and put that together. So I've got this equation for what V is, and I've got an equation for what E is. I'm going to plug those into Euler's formula, which I'm sort of assuming is true for now. Okay, so we're going to take the equation V minus E plus F equals 2, which is true for all the Platonic solids we found so far. We're assuming it's true for any more that might be out there. Okay, and I'm going to plug in the expressions that I found. Fn over m minus Fn over 2 plus F is equal to 2. This is for a Platonic solid, the one that I've been describing, with all of its faces the same regular polygon, and all of those polygons meeting in a sensible way at each corner, the same number meeting in each corner. Okay, I can rearrange this a little bit. This is, so I could multiply it by 2 times m to get something like, I can take out the factor of f, and I can multiply up. I want to kind of get an equation out of this, I think. So 2n minus mn plus 2m is equal to 4m. Okay, so this is starting to look like an equation for how many faces I've got. Move the mouse around with the right button. There we go. They've also changed how Miro works over the holidays. Okay, this is starting to look like an equation for f. Okay. In fact, the bottom bit of this is pretty close to factorising. I never know how much people have seen about factorising, but I can slightly factorise it because it's got this kind of mn term, which feels a bit like m and n multiplied together. It's got these separate bits that feel like m and n have each been multiplied by 2. So this feels a little bit like, I could work out something like m minus 2 times n minus 2, because that's mn minus 2n plus 4. You can tidy up this thing on the bottom down here by writing it like this. I am skipping some algebra to prove that these two things are equal. Homework, maybe check that these two things are equal to each other. Okay, but this is really exciting now because I've got this nice expression for what the number of faces is for my Platonic solid. Whether it's a real one or not, I suppose. I need to have the number of faces equal to 4 times m over 4 minus m minus 2 m minus 2. Okay, crazy. Right, this is an expression for how many faces a Platonic solid has in terms of m, how many faces meet at each point, and n, the number of edges on each face. Okay, it's sort of maybe surprising that such a formula exists, but here it is. This is true for all of the ones we found so far. If you go back and check for all 5 Platonic solids, they work in this formula. And something you notice when you're doing that is, well, I suppose this thing that I'm working out, 4 minus this stuff, has to be positive. It's positive when you work it out for the other 5 Platonic solids, but more importantly, this must be positive because the number of faces is positive, and 4 times m is positive. The number that meet at each point is positive. So I've got a positive thing on the left, and I've written it as positive thing divided by this stuff down here. Aha! Okay, so that thing there must be positive as well. And that seriously limits the possibilities for what my Platonic solid could be. Because to get a positive f over here, I need to take this positive 4m and divide it by a positive thing. But hang on a minute, when I work out this expression, it's only positive if m and n are quite small. So I need m and n to both be quite small. Let's make that precise. I need 4 minus m minus 2 n minus 2 to be positive. I need 4 to be bigger than m minus 2 n minus 2. These things are whole numbers. So I need m minus 2 times n minus 2 to be equal to, I guess it could be equal to 3 or 2 or 1 or maybe even 0. I don't think it can be 0. I don't think it can be negative because m and n are both at least 3. So 3 or 2 or 1. And so this gives me some cases. And then I can think about the possibilities in each of these cases. So if n minus 2 times n minus 2 is equal to 3, well, there's not that many ways to factorise 3. This one turns out to mean that, so in that first case, n minus 2 times n minus 2 is 3. So that can happen when the first bracket's 3 and the second bracket's 1, or the other way around. So this could be n equals 5, n equals 3, or n equals 3, n equals 5. So that's a couple of solutions. n minus 2 times n minus 2 could be 2 if one bracket's 2 and the other one's 1. So that would be n equals 4, n equals 3, or n equals 3, n equals 4. Or this product could be 1 if both brackets are 1, and that would be n equals 3, n equals 3. Okay. Those are all the possibilities. Okay. Those are in fact all the possibilities, because everything's a whole number. The whole number's really split up the possibilities of what I can do here. So that gives me 5 solutions. These 5 solutions exactly match up. Still catching me out with the pattern being different on the Miro. Anyway, these 5 possibilities exactly match up to the 5 Platonic solids that we already found. Okay. Crucially, because this item in the middle, 4 minus n minus 2, n minus 2, has to be positive. Okay. Good, right, okay. So quick proof that there are exactly 5 Platonic solids if this thing's true. V minus E plus F equals 2. Okay, so I feel like we're back to that. Understanding why that's true is sort of a key thing. And it's true for convex polyhedra, but it's not true for some other shapes. People have been putting some of them in chat. Excuse me. And Raf spotted that they kind of turned up in pairs, right? They kind of turned up with the 3-3 solution on its own at the end. Is the tetrahedron, and these MN pairs. M and N are just switching the roles of faces and corners. So they do turn up in their dual pairs as well. Okay. Why can't n minus 2 be 0 or negative number is a really good question that I should have written something on board. Fine, okay, if this is 0, then, well, m or n, so I suppose, how would you make this 0? M equals 2 or n equals 2? But the problem with this is, well, there are 2 problems with this. One is that n equals 2, n was supposed to be how many sides the shapes had. Triangles, n equals 3, squares, n equals 4. N equals 2 makes me a bit sad because those faces have only got 2 sides. So I don't really like that. And m equals 2 says that you've only got 2 faces meeting at a point. Which doesn't actually give you a solid, it gives you a flat thing. So this shape is kind of flat and made out of, or it's either flat or made out of things that don't have any area on the faces. So that's sort of bad news either way around. It can be negative because that's sort of even worse. M or n would have to be, one of them would have to be even smaller. Okay. SV is redefining pointiness along the way. You do something F affects the area of a section into the polyhedron. So thinking about sections as you slice down, I think that is related to the idea of how much sphere they take up. And then you could do a function of that if you like, I suppose. Yeah, okay. It's a bit like defining angle by... You can define angle in terms of the area of a triangle, the area of a little isosceles triangle, or the derivative of that if you want to, I suppose. These things are all related. They're all functions of each other. Okay. Good. Right, okay. What do I want to do next? I had a plan. The plan had a break in it. We're 10 to 6 now. Do you want a break? I kind of feel like we should talk about this V minus E plus F thing. So traditional maths club that we have some sort of ad break. The ad break is a chance to catch up with chat and to give you an addition problem. During the ad break, I'd like to think about what happens to this number V minus E plus F. So all it says is this is true for convex polyhedra, ones that kind of feel like spheres, that kind of don't have any weirdness going on. For the ad break, joining stuff together. Andrew Wiles in chat says, I was missing the beginning, sorry, because I was proving Fermat. Yeah. Fair, we've all been there. What's going on? Can someone fill me in? So we've been looking at some Platonic solids. There are 5 Platonic solids. They've got very nice faces and corners and edges joining up the corners. There's exactly 5 of them. We've done a little proof that there are 5 of them. Using this fact that I haven't proved, that for any convex polyhedra, that's a shape made out of faces glued together into something that looks a bit like a football, the number of vertices minus the number of edges plus the number of faces is always 2, which we haven't proved. For the ad break, we're thinking a little bit about what might happen if you glue 2 of those together. That was not quite explained like I'm 7. It was maybe explained like I'm 16, watching the maths club, sorry. Okay, cool. There's this idea about gluing things together. Cool. So I've put this as the ad break problem, the kind of gluing things together, because this idea of gluing things together gets us a little bit closer towards topology, which is where I'm going with this. I think somebody called this earlier. This feels a bit like topology. This operation of gluing things together is something that we sometimes think about in topology. I'm going to try and draw a picture of what I'm thinking about for this. I'm imagining you've got a shape, maybe it's got lots of triangular faces on it, but it doesn't have to be one of our Platonic solids from before. Maybe it's got some squares over here as well. Maybe you've made your shape by gluing a kind of triangle sort of array with a square at the top here, and maybe a pointy bit down here as well, or like that. Very nice. Okay, I've invented my own polyhedra, which I'm going to name after myself. This is the James polyhedra, and it's got this kind of triangle on the end. And if I check, then this one does have v minus e plus f equals 2. A better teacher than me would actually go through and count. I should count, shouldn't I? Okay, right, here's the James polyhedra. It's got these corners at the back, don't forget about those, and then it's got corners around here. Don't forget this edge. Okay, and I put a whole mess of triangles on the front. Can I remember how they work? Yeah, there's this kind of square face at the top. I've designed my own polyhedra, and then got carried away a bit. It's got this kind of square face on the top, which I don't want to forget about. Okay, I'm going to colour it in purple. And this face at the back, which is a bit curved. Yeah, I think it's also got a square face going on at the back over here. Okay, let's count this. Count its vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 vertices. And it's got a whole load of edges. 1, 2, 3, 4 around the back, and then 1, 2, 3, 4 coming out, so 8, 9, 10, 11, 12, and then I stuck on 13, 14, 15 along the top, 16, 17, 18, 19, 20, 20, like that, I think. How many faces has it got? It's going to be amazing if this turns out to be 2 at the end. I've drawn a terrible picture of a polyhedron, and if you've just joined us, I've drawn a terrible picture of a polyhedron, and I'm trying to demonstrate that it's got v minus e plus f equals 2, which is tricky because I've hidden a bunch of edges round the back, and I'm just counting them again. 1, 2, 3, 4, 5, 6, 7 on the top, and then 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 maybe, 20-ish. And it's got some faces. 1, 2, why have I done it like this? 3, 4, 5, 6, 7, 8, 9, 10 maybe? Goodness me. Okay, I've lost confidence that I can describe what the back of this shape looks like. Cool, right. Moral of the story, don't draw shapes live. I should have prepared one. Okay. Let's try and draw a better picture of this shape that I'm imagining. If you've just joined us, then nothing happened just now. It's all fine. Everything's fine. How are you? How's your day going? Here's a shape that I've designed, and I'm going to draw it properly now. It's a cube, but then I've stuck some triangles onto it on, let's say, this face here. People in chat are going to tell me that the previous one was just fine. Okay, I'll put a very long triangle face on that side of it. Okay, that's an exciting shape. Okay. Okay. So let's try and work out what v minus e plus f is for the James shape, which I've now drawn a much better picture of and I'm feeling much better about. Okay. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 vertices. It's got some edges. It's got all the edges that the cube had. It's got all 12 of those, and then I've added on 1, 2, 3, 4, 5 edges on the other side. So it's got 17 edges. How many faces has it got? Well, it's got 1, 2, 3, 4, 5 faces from the cube, and then it's got these 2 long rectangle faces, and then 2 big triangle faces on here. So I think it's got 9 over here as well. If I put those in, oh good, then I do get 2. Brilliant. This v minus e plus f fact holds not just for Platonic solids, but for shapes that are made out of a mixture of different faces. The faces don't have to be regular shapes. Overall, the object, there are some rules about what the object has to be like. I'm using the word convex in here. Convex means that you could blow it up to a sphere. You could kind of inflate it to a sphere, I suppose. Cool. Okay, Andrew Wiles, I think I need you to calm down a bit in chat. Thanks. Cool. Good. Good. Right. Okay. So, question that I've put on the ad break is: what happens if you glue 2 things together? Maybe you've got 2 of these, and you glue them together by taking, so leaving the pointy bits, leaving the pointy edges alone, and taking the square faces on the backs. You want to join these together. I've got this one slightly slanted, I suppose. What you could do is you could stick these together. Oh, come on. Stick these together by taking this face and taking the back face on this one and gluing them together. So taking those squares, mushing them together, and getting rid of the interior faces on the inside to make one new shape. And when you do that, well, what will happen is I will have all of vertices, edges and faces from before, except, okay, so this one had v minus e plus f equals 2, and this one's also got v minus e plus f equals 2. So beforehand, if I count all of the vertices, edges and faces from before, all of that v minus e plus f will be 2 for each of them, so if I add them together, well, before I glue them together, v minus e plus f will be, I think, 4, because instead of 10, 17 and 9, I have 20 vertices, 34 edges and 18 faces before I do the gluing. And then when I do that gluing to stick together these square faces, well, what will happen? So I'll lose 4 vertices, because when I glue my squares together, I'll start with 8 corners for my 2 squares, but then after I've glued them, that's only 4 corners where the squares are now glued together. So I'll lose 4 corners. I also lose 4 edges, because I've taken the edges of one of my squares and matched them up with the edge of my other square. And I also then get rid of 2 faces. There's 3 things happen. I lose some vertices by doing the gluing, I lose some edges by doing the gluing, and I lose 2 faces by getting rid of the 2 faces so that I can glue these together into one shape. If I do that, then I started with my 2 objects with v minus e plus f equals 4. Once I've done the gluing, then I lost some edges, I lost some vertices, but they cancel out, and then I lost 2 faces, so I go down from v minus e plus f from 4 down to 2. Right, okay, pretty complicated. There we go. But we do end up with, after I've glued this together, I get a complicated shape, which also has v minus e plus f equals 2. Okay, so adding these things together. Right, yeah, now there are lots of problems with what we've just said. Someone's put one of them in chat already, which I love. Let's talk about some problems, because I can't stop there without talking about shapes which don't have v minus e plus f equals 2. So let's do a quick think. We've already seen that this is true for Platonic solids because we found all of the Platonic solids, and well, we found all the Platonic solids, and then we did a weird computation where if this is true, then it's true, I suppose. So if v minus e plus f equals 2, we found all the Platonic solids. Euler says that it's true for all convex polyhedra. So anything that's kind of a bit like a football, kind of spherical in shape. But there's lots of examples of things where v minus e plus f is not equal to 2, which some people have thought of in chat. There are things like, if you take a donut shape, like this donut shape, and you build a polyhedral model of this, so you build some sort of polyhedra by sticking together triangles very carefully, all the way around to build this donut shape, then what you find is this has v minus e plus f is equal to 0, which is not 2, and which looks like a donut, so that's easy to remember. And in fact, Grace in chat knows a fact that if your shape is a bit like a donut but has more holes, so there's a picture to draw here, then the rule is in fact that you subtract 2 for every hole you get. So this shape's a kind of double donut. If you build this out of triangles, so I'm kind of mean that literally, if you get a bucket of triangles, those plastic triangles that you can get that stick together, and if you stick them together to build a model of a double donut like this, and then count all of the faces, or count all the vertices, edges and faces, then you get v minus e plus f is minus 2. Okay, and you can keep going. You subtract 2 for every hole. Cool. There are other examples of things that go wrong. V earlier said in chat down there that when you do this sticking operation, something that I said was kind of a bit like when you do the stick together, when you stick them together, do you end up with something that still has kind of ring of edges going on, but no face in between? This is what I want to be true. So nothing in between. I get something like this. Or do you consider these top bits to be one big long face because they happen to line up? So you can run into problems like that. There is a name for a number of holes, and I'll put it in the further reading, but there's a word here to Google which is genus for that. Okay, if you put a square section of plane into 3D space, I don't think you get Euler characteristic 2. Okay, so if you just have a square, cool. We can argue about whether this is a polyhedra or not, I suppose. But if you just have a square, just a square on its own, it has, well, I'm not even sure how many faces that's got, but maybe that doesn't do v minus e plus f equals 2. Interesting one. So if you take, related to this idea that v had, maybe is this one face or 2, if you take a cube and you stick a smaller cube on top, not in the way that I was describing before with the gluing, but if you just sort of glue it to the top in the middle of one of the faces, then what you find, try and draw the back bit, okay. What you find is that, well, you've got one very strange face now. One of your faces here kind of looks like a square with a little square removed. How does that work? It turns out to have v minus e plus f is not equal to 2 for this shape, because one of your faces looks like this with a hole in it. So actually, the reason I've been dodging around what the kind of true statement is because the actual statement of which shapes have v minus e plus f equals 2 The answer's a lot of them, but it's not everything you can make out of triangles. It's not every polyhedra. And you have to be really careful to describe what you mean by face, what you mean by polyhedra, what you mean by sticking things together to make a shape. What is a shape? It's something I really like, because the more of these examples you think of, the more you have to go back and question, well, what did I mean by a vertex in the first place? I've done this whole hour without defining any of these things, because it's playing around with examples like this that helps you find out, well, what was the right definition? What did I actually mean by polyhedron in the first place? Okay, so I'm going to leave you on this pretty unsatisfying note, but put things in the further reading, I think. Further reading is going to have more to look up for other interesting shapes that maybe have v minus e plus f equals 2, or maybe don't. And I'll put in the answer as well for what the precise definition is for when shapes have v minus e plus f equals 2. Further reading coming out on Friday. But I think I'm going to stop the Maths Club bit of the live stream there. Cool. I think that's what I wanted to talk about. Okay, right. I hate the people who joined in the middle and said, what on earth's going on here? I'm not sure you really got an answer, but never mind. Okay. When do the math scores get sent out? So, quick admissions bits that I've seen in chat so far. Math scores are getting sent out after Oxford decisions next week. So if you're watching live, emails are going out, I think, by the end of next week. I think decisions are going out Tuesday, so then emails Wednesday, Thursday. Decisions have been made. We are working out how to send out all of the emails next week. As with decisions before, emails get sent out by the different colleges, so they're not all going out to the same time to everyone. Please be patient with the emails going out on Tuesday, and I think UCAS gets updated as well at some point, so you might see something on UCAS at the same time or before or after you get contacted by Oxford. Okay. Yeah, Dirichlet knows stuff about CW complexes. Cool. Okay. Complexes is a kind of generalization, I think, of some of the things we've been talking about. Good. Books that I'd recommend. Since we've been talking about topology, interesting books thinking about other dimensions. Things like Flatland is just really great for a little bit of topology. It's quite a strange book. There's a sort of sequel, called Flatterland that has a bit more maths in. I'm mentioning them because we've been talking about topology, and we've had Flora on previous episodes of Maths Club who talks about topology and always recommends Flatland and Flatterland as two books. And Romana Jan wants to know tips for thinking of applying for Oxford for maths in the future. Think about bits of maths. Think about maths outside the classroom. Try and find other bits of maths that you like, and just find out other stuff, I think. Is the right thing to be doing now if you're thinking about applying to Oxford in the future. Don't worry about admissions process, application details, stuff. There are some deadlines. It'd be good if you looked up when the deadlines are and you're aware of those. But the best thing you can do in sort of year 12 or younger is try and find other bits of maths to think about, as well as the stuff that you're doing in the classroom. Okay, books for someone applying for CS. I think with CS, I think the main advice is try and practice getting a computer to do some things. If you can get a computer to solve some problems for you, I think it's a really good skill to have. So these days there's lots of online guides to learn to code a little bit, but really it's learning how to get a computer to do what you want it to do to help you solve a problem. Maybe the computer's going to check lots of cases for you, or maybe it's going to help you by doing some calculations that you don't want to do. But if you can find out how to get a computer to do that sort of thing for you, I don't have a preferred programming language or anything, but I think there's lots of guides out there for learning how to get computers to help you solve problems like that. Yes, semicircular prism, yes. Cylinders are really interesting. I'm glad someone's mentioned cylinders. So a cylinder, right? It's got one curved surface here. It's got edges equals 4, maybe 4 edges. No, 2 of those are just in the picture, right? So just 2 edges, one at the top and one at the bottom. And hang on, that's faces. Sorry, it's got 3 faces, 2 edges, and then maybe at the vertices is like 0, infinitely many. Where are the vertices? Has it got any vertices? So then working out what v minus e plus f is, sort of I don't really know. I don't think there are any vertices on this shape. So cylinders are sort of a bit weird. Cool, good. Did we do a whole OOMC without any basic arithmetic mistakes? I think we got pretty close during the bit with the joining together the two James solids, because I couldn't even draw one of them. Cool. Is it a good idea to apply to Oxford with A*A*, Maths, Further Maths and Computer Science? If you're applying for Maths, those are exactly the grades that we're looking for. So, yeah, sure, if you want to study at Oxford, then those are sufficient grades for Maths, Further Maths and Computer Science. Yeah, cool. Those are really good grades. Congratulations if you've got those grades. Or if those are your predicted grades, then you're on track to achieve great things. Oxford doesn't need 3 A stars, if that's the question. Oxford doesn't need a 4th A level, doesn't need the 3 A stars for Maths at Oxford, or Computer Science. We're much more interested in how you solve problems and how you the A star in Maths and Further Maths, which is pretty good. Cool. Skeleton of a cube without the faces filled in. Right, so is that a polyhedron, right? So sort of mainly the category of things that we're trying to describe is polyhedrons, and the skeleton of a cube without the faces filled in. So this is kind of not got. Is this your example for something that's not got any faces, but it's still got all the vertices and edges? It's a bit cheeky, isn't it? You've kind of removed all the faces. But yeah, I suppose somewhere where the way to fix this is to go back to, well, I was talking about for some sort of polyhedra, and to try and talk more about what polyhedra is. There's big question marks over what sum means in that statement, but what does polyhedra mean as well? That also gets a question mark. What's a polyhedra? Does it have to have any faces? One that I like to throw in at some point during this is, what about the polyhedra that's got no faces and no edges and no vertices? It's just the empty set. Feels like it does a lot of the same things as polyhedra, right? Every edge goes between 2 vertices. That's true if you've got no edges, because then if you've got no edges, every edge goes between 2. Every edge does anything you like if you've got no edges. Every face is a regular polyhedra. Every face is lovely if you've got no faces. So I kind of feel like no points at all should somehow count. But of course that's got v minus e plus f equals 0, because all the things are 0. Maybe it doesn't really count. Spider-Man wants to know if they take second college interviews. So this is during the Oxford admissions process. If you're interviewed, you usually get interviewed by a second college as well. And the first college people can see what happened. Well, they can see the scores from that second college interview as well, and they're allowed to take it into consideration. They're allowed to look at the kind of average. Of course, they were there for the ones that they interviewed you for. So they can see the grades, but they're allowed to take them into consideration or not. There are sometimes brief comments on them as well for somebody to say this one didn't go very well, or we're aware that some people have interviews that go well and interviews that don't go well. Cool, right. Matt or Tamua, if you're not applying for Oxford but unis like Bristol, I can't advise you on admissions for Bristol. Sorry. Part of my job here is admissions for Oxford. Unfortunately, I can't comment on the other universities. If you have Maths and Further Maths, is Chem alright as your 3rd A level? If you want to do Maths, Maths at Oxford, we are fine with Maths A level, Further Maths A level, and then any 3rd subject. We don't mind. You've got Maths and Further Maths. That's enough maths. You don't need the 3rd one to be mathsy as well. Your 3rd A level could be anything. Chemistry is fine. That's in writing. If you want that in writing, it's somewhere on our website. And if you search for a standard conditional offer or something like that, if you want that in writing rather than someone on a live stream saying it and giving you a thumbs up. But yeah, chemistry's fine. Infinite polyhedra, says Dirichlet. Right, so I've got my empty polyhedra that's got no faces, edges, or vertices. Dirichlet would like an infinite one, that I suppose maybe it's like a cube but really long. So a really long cube would be like this, and then it's infinite, and that's Dirichlet in chat has come up with that as something which I suppose has got some very big faces, but it gets away from having those edges at infinity. And then Dirichlet also says or fractals, which I feel like we're getting a little bit away from any sort of description of what polyhedra might be, and now thinking more about just some stuff. I really don't claim that v minus e plus f equals 2 is not true for all objects. it's only true for, we've thought about things that don't have faces or things that go on forever or are a fractal. It's really only true for some polyhedra. Right, cool. V thinks that you can't completely remove the cube's faces. Those lines of edges, you're going to end up with more faces. And I suppose there is a definitional difference here, like whether you have this collection of edges and faces which are independent, and whether it's okay to just remove the faces and talk about the edges on their own, or whether the edges have to be the edges of faces. Now V, I think, believes that the edges have to be edges of faces. I think my definition of polyhedra, if I was forced to write down a definition of polyhedra, which I've avoided doing, I would say, I think I'm with V, I think the edges have to be the edges of faces in a polyhedra. But my definition is going to be a bit weird like that. Infinite flat tiling, should that count as a regular polyhedra? So polyhedra normally means a three-dimensional shape, so I'm not sure I'm going to go with your infinite flat tiling, but I like infinite flat tilings. The infinite flat tilings all have v minus e plus f equals 0, I think, or is it 1? Can't remember. Well, they're all infinite, so it's a bit tricky. But if you draw a finite bit, a finite flat tiling, and I think that has v minus e plus f equals 1, whatever you do, even if it's not a regular tiling. I think that's true. Rilo wants to know, does it just count as a shape with a hole in it? I think that's optimistic. I'm not going to go that far. If v minus e plus f equals 0, I don't claim that if v minus e plus f equals 0, then you're a shape with one hole in. I think there's other weird stuff going on. Cool. Were decisions made over Christmas? We actually made most of the Oxford decisions by a couple of the week before Christmas. We had a big meeting with all of the colleges together, having massive arguments and deciding who to make the last few offers to. But that was week before Christmas. Does Oxford look at GCSEs? It's fun having these discussions with people at different ends of the admissions process. People who have just gone through and are waiting for final decisions, and people who are about to start. Oxford doesn't have a minimum number of GCSEs for the maths course. We don't have a minimum standard in GCSEs. We do look at them. We look at your achievement in GCSEs. Although we know that during the pandemic, GCSEs have been a bit weird, and the grades from GCSEs are not as reliable as they were normally. So we changed our processes a little bit behind the scenes to rely less on GCSEs. We weren't relying on them very much before. We were looking at them, but we know that even now, looking at the GCSEs doesn't tell you very much. So we get the data, and we always look at the data, but we know that the GCSE data has been a bit strange for a couple of years now. Cool. When are we next live? We're next live next Thursday. We're doing this weekly. We're live every Thursday at 5 o'clock. And it's not just me. I'm going to get current students and staff on as well, to take in turns explaining bits of maths. I should have said this at the start. Today's been a bit of a tech demo, working out, can I show things on screen for a live audience? And throughout the term, we're going to be doing other stuff as well. Okay, what if we put line segments on and we just have random floating line segments, like a kind of aerial coming off the side? Is that a polyhedron? I think that's not a... So my definition of polyhedron probably has to ban that, because there's kind of an edge just over here, and the edge doesn't belong to any faces. I'm starting to come around to the V's definition where the edges have to belong to this. Cool. Recursive, some sort of recursive formula, and find out what happens. Looking at fractals. I mean, have a go if you like. Fractals tend to involve going to infinity and having very complicated details, which then probably makes the number of edges a very complicated thing to think about for a fractal. In fact, fractals are famously... Well, people famously talk about fractals for things like the coastline, to say, well, the edge is actually very wiggly, so that's like an infinite number of edges, right? So we're going to have trouble defining V, E, and F, I think, for fractals. Cool, right. Thanks for watching. This has been a bit of a messy live stream while I work out the tech again and try to remember how to do this and get used to a slightly different setup. We're going to be back next week to talk about something completely different, and I'll see you then at 5. This is going to be available on our YouTube channel. They're going to stay up straight away afterwards. You can watch back. There are about 20 of these from last year. Most of them much more polished and better presented. Most of them with other people involved. About 20 of them if you want to watch other episodes out there. And we'll be back next week at 5 o'clock for another one. Thanks for watching. Take care. I'm going to hang out and chat for a little bit over in Slido afterwards, answering, because I can type faster than I can talk, and I've started to ramble quite a lot. Yes, time to stop talking. Thanks for watching. Have a nice evening. Goodbye. See you next week.